Good day. This paper is titled A Numerical Investigation of the Effects of Rear Spoilers' Varying Angles and Heights on Cars' Aerodynamic Performance Using Sim Scale, presented by Bukaco Christian Donald, Garcia Rian, Silva Ethan Theodore, Tenorio Patrick Kevin. Good day. My name is Patrick Tenorio and I'll be reporting Chapter 1 Introduction. Overview and Background. The automobile's performance and safety are the primary concern of engineers tasked to design them. Proper aerodynamic design of the vehicle is important. Parameters like drag and lift are needed to be observed to reach the optimum performance of the vehicle. When a vehicle is moving, various aerodynamic elements are being experienced by the car, like the drag, lift, and the downforce as seen in the figure. The drag force acts horizontally and competes against the forward motion. For the lift force, it acts vertically where the pressure under the body of the vehicle is observed. Proper aerodynamic lift force is observed to increase the stability and handling of the vehicle. When the lift force is greater than the downward force, the vehicle moving would be prone to accidents. Modern vehicles nowadays can reach faster speed, experiencing higher uplift force, which is why an external aerodynamic device like the rear spoiler is proposed to be used to provide stability, safety, and to prevent unexpected accidents. There are different kinds of spoiler, but for this study, the researchers will solely focus on the use of the rear spoiler. The rear spoiler is a wing-shaped external component device which is installed at the boot or rear part of the vehicle as seen in the figure. Traditionally, to determine the capabilities of the design spoiler, it requires at least 3 hours in a wind tunnel, although nowadays computational fluid dynamic simulation or the CFD simulation are proposed to be used in determining the nature of the airflow happening around the vehicle, since it saves a lot of time and the money for the study. Common problem encountered by people who wants to incorporate a rear spoiler on their car is that the rear spoiler they bought is not suitable for their vehicle. Instead of improving the car's aerodynamic performance, a rear spoiler that is not properly designed will just make it worse. Every car model has a different rear spoiler for them. They are different when it comes to height, angle, length, and width cord. There are still no studies that tries to assess the effects of different angle at different height of a rear spoiler on drag and lift coefficient of the car. It is apparent that a more intensive study should be conducted to determine how these two parameters, height and angle, could correlate to each other. General objectives. The general objective of this study is to first configure the rear spoiler that will improve the sedan's car model's drag and lift coefficient, and second, to show the effect of different angle at different heights of the configured rear spoiler on the drag lift coefficient of the sedan car model. Specific objectives. The first specific objective is to configure a flat plate rear spoiler based on Mustafa model. Second is to perform CFD simulation using sim scale to determine the drag and lift coefficient of the car with and without a spoiler. Third is to determine the spoiler's angle and height setup for the lowest drag coefficient regardless of the lift coefficient and the lowest lift coefficient regardless of a drag coefficient. And lastly, to analyze the drag and lift coefficient of a rear spoiler setup simulated in this study as the speed increases from 80 km per hour to 120 km per hour. Significance of the study. This study shows the relevance of using a rear spoiler in decreasing the drag and lift induced in a car. It would give readers an idea of how properly configured rear spoilers should look, as well as how parameters like the rear spoiler height and angle could affect the aerodynamic forces induced in a sedan car, such as the drag and lift forces. As the researchers use SIM-scale CFD simulation tool to study the effect of different combination of rear spoiler height and angle on a car drag and lift coefficient, the readers would also learn best practices for external aerodynamic simulation. Scope and limitation. The first scope and limitation, the researchers will use sim scale CFD simulation to show the effects of rear spoiler to the aerodynamic forces drag and lift induced in a sedan car. Second is to evaluate the drag and lift coefficient of sedan car different combination of rear spoiler's height and angle. Third is to set the speed at 80 km per hour, 100 km per hour, 120 km per hour for all simulation setup. Fourth is to assume the fluid to be in steady state condition. This means that pressure and velocity variation and the aerodynamic coefficient will remain the same at any point of time. Next is to assume the fluid to be compressible, the speed not exceeding a Mach number of 0.3 or 100 meters per second. This study doesn't have an actual experimental result. Since this is only a simulation study, the researchers cannot assess the accuracy of the result because the researchers do not have an actual experimental result. Lastly, the change in fuel economy with respect to the change in drag and lift coefficient of different setup is not part of the study.
My name is Christian Donald Bojaco and I'm going to present to you our Chapter 2, Review of Related Literature. Computational Fluid Dynamic Analysis of Passenger Vehicle at Various Rear End Spoiler. In this study, the impact of the rear spoiler is investigated with the use of computational fluid dynamic software. This study points out that the shape of the automotive vehicle affects the fuel consumption of the vehicle by 3% in urban driving and 11% for highway driving. The simulations that was performed in this study mainly focus on the generated drag, lift, and pressure distribution with the corresponding angle that was placed. This study concludes that from a designated spoiler height, the smaller angle with wind collision shows higher drag force being generated. The spoiler with the smaller angle of wind collision creates smaller zone for a turbulent flow behind the rear end of the moving vehicle. The coefficient of lift in this study has been sustained to achieve excellent stability for the high-speed moving vehicle. Experimental study of the combined effect of spoiler height and diffuser on aerodynamic coefficient of a generic car. Experiments using aerodynamic devices, specifically the spoiler and diffuser, was performed in this study. Reducing the aerodynamic forces in the rear part of the vehicle is the main objective of this study. The speed was also a factor in this study, maintaining the speed at 0 to 60 meters per second and a constant speed of 60 meters per second. The given table shows the different spoiler setups for this study. It is concluded that the fourth setup was the most effective way to position the spoiler, thus increasing the height for the spoiler will decrease the lift force on the vehicle, making it more efficient. The figures below show the velocity versus lift and the velocity versus drag of the experiment. It is concluded in the study that installing a spoiler and a diffuser will decrease both the lift and drag force in the vehicle. The height of the spoiler was a big factor in decreasing the values for the two factors considered in this study. It is noticeable that as you increase the height of the spoiler, the resulting values for the drag and lift improve. The inclusion of the diffuser in this study was not conclusive because it was constant in all setups. Aerodynamic analysis of rear wings and rear spoilers of passenger automobile. Simulation of the aerodynamic performance of the rear spoiler, rear wing, and the conventional automobile without an external aerodynamic device is analyzed and compared throughout the study. Throughout the simulations, 5 different velocities are tested for the scenarios of the conventional automobile without an external aerodynamic device, conventional automobile with rear spoiler, and conventional automobile with rear wing. The figure shown shows the conventional automobile without external aerodynamic device, while the next figure shows the conventional automobile with rear spoiler and rear wing. The researchers were able to explain the results further to the readers by creating a lift and drag coefficient versus velocity graphs as shown in the figure. During when the rear spoiler is attached to the automobile in the simulation, a constant reduction rate of 24% in the lift coefficient were collected for the 5 velocities, while the highest reduction rate for the drag coefficient is found out to be 9% during a velocity of 100 kilometers per hour. From the flow analysis, the researchers were able to confirm that the use of a rear spoiler can delay the flow separation at the rear part of the automobile. The flow separation of the conventional automobile without an An external aerodynamic device appears to lessen and almost disappear, thus preventing the increase of the drag coefficient in the vehicle. The researchers were able to conclude through the observations and data collected in the simulations that the use of the rear spoiler or a rear wing can be beneficial for a conventional automobile at high velocities. The figure shows the velocity flow analysis over the conventional automobile without and with a rear spoiler at 80 kilometers per hour. Investigation of drag and lift forces over the profile of car with rear spoiler using computational fluid dynamics. The focus of this study is the reduction of drag force at the rear end of the car by using a rear spoiler that will improve the fuel consumption. During this study, ANSYS computational fluid dynamic simulation is used to determine the drag force experienced by the three vehicle setups and different velocities variation. A sedan type of automobile is the model used in all simulations. The figure shown from left to right shows that the rear spoiler dimensions from the first setup, the rear spoiler dimension from the second setup, and the generic car model dimensions. The three different setups that were tested in the simulation is the vehicle without a rear spoiler, a vehicle with a rear spoiler with a height of 28 cm above the surface of the rear end, and a vehicle with a rear spoiler with a height of 0 cm above the surface of the rear end. The researchers were able to conclude that the setup with the rear spoiler with a height of 0 cm has the best result compared to the two setups performed in the simulations. When the velocity increases, it is found out that the rear spoiler with a setup of 0 cm has the best drag coefficient of 0.329 and lift coefficient of 0.106. The utilization of the rear spoiler shows that the aerodynamic drag force is reduced, which affects the fuel consumption of the vehicle for the better. It is found in the study that approximately 2.18% the drag coefficient is reduced when a rear spoiler is utilized. The figure below shows that the comparison for the drag and lift coefficient from the three setups when the velocity increases. Performance of NACA-cambered and symmetrical airfoils as rear spoilers on race car aerodynamic drag and lift computational fluid dynamics study. In this study, the computational fluid dynamic is used to analyze the aerodynamic effects of NACA 2412 cambered and NACA 0012 symmetric airfoils as rear spoilers. It is calculated that the speed of the automobile exceeds 80 km per hour. The aerodynamic drag became a main source of resistance. The researchers used three types for the 10 sports car models that were developed using SolidWorks 2017. 8 NACA 2412 and including NACA 0012 airfoil spoilers were attached to the model with an angle attack of -6, -3, +3, +6 degrees. The researchers used ANSYS Design Modeler to simulate the wind tunnel around the automotive. The maximum lift decline was achieved by NACA 0012 spoiler on the angle of attack -3 degree. The drag increases in all cases except for NACA 0012 on the angle of attack +6 degree. Below shows the overview of the percentage variation in the drag coefficient and lift coefficient values for NACA 0012 rear spoilers. The researchers then conclude that the NACA 0012 airfoil performs much greater than the NACA 2412 as a rear spoiler. Moreover, the spoiler increases the stability and fuel efficiency of the vehicle as the speed increases. Computational fluid dynamics study on aerodynamic effects of a rear wing or spoiler on a passenger vehicle. In this study, the researchers used ANSYS Fluent to simulate the aerodynamic effects of a rear wing or spoiler on a passenger vehicle. The researchers was able to perform numerical simulations on the vehicle using computational fluid dynamic techniques. The study was divided into three different setups. Case number 1, vehicle model without rear spoiler. Case number 2, vehicle model with the first rear spoiler design, which is the left figure. Case number 3, vehicle model with the second rear spoiler design, which is the right figure. Before conducting the main experiment, the researchers conducted a convergence test to ensure that the values gathered were accurate and realistic. According to the results obtained by this study, adding a spoiler to the vehicle reduced the drag coefficient and the lift coefficient. The first spoiler provided the vehicle with the best drag coefficient of 0.192, while the second spoiler provided the best lift coefficient of negative 0.268.
Hello, my name is Ethan Theodore S. Silva, and I will now be reporting Chapter 3 Theoretical Considerations. SimScale is founded in 2012, where it started only as an engineering consultancy company. This simulation platform is accessible to all who has internet connection. Installing the software in the computer is not needed anymore because this is based on cloud computing that will not be needing any random access memory or RAM usage on the computer. This simulation software allows finite element analysis, computational fluid dynamics, and thermal simulations. Autodesk Fusion 360 is a product software of Autodesk that is used for 3D modeling, which comes with parametric integrated feature-based CAM module that is built in the software. Autodesk Fusion 360 combines the mechanical and industrial design, simulation, collaboration, and machining. The computational fluid dynamics is composed of methods that can provide solutions to problems of fluid dynamics and heat transfer. As shown in figure, the disciplines of CFD that are used to accurately assess the problems are primarily computer science, engineering fluid dynamics, and mathematics. This numerical method is commonly used in simulation and computational fluid dynamics. It transforms partial differential equations into discrete algebraic equations based on the conservation laws. This method was responsible for the discretization of the geometric domain that provides mesh solutions by integrating the partial differential equations that generates finite or controlled volumes in the domain created in the simulation. During simulation, nodes are generated on surface to serve as the center of the finite volume, the boundaries of which are determined by connecting the centroids of each surface as shown in the figure. The element solved by this method to create a finite volume mesh is essentially a polyhedron. During simulation, three-dimensional mesh was used and the shapes that were commonly used are seen in this figure. Automobile aerodynamics. The principle of aerodynamics is not only limited to flying objects, it is also applicable to cars where air also travels around its body. There are two subcategories for aerodynamics, the external and the internal aerodynamics. The external aerodynamics would be the focus of our study, and it is the study of air that goes around the body of a specific vehicle. It will focus on the drag lift forces that is acting on the object. Okay, moving on, the rear spoiler. This type of spoiler is an external aerodynamic device that's attached on the rear back part of the automobile. Its main purpose is to spoil the unwanted air movement that is happening across the vehicle. Spoilers are usually used in sports cars to reach optimum performance, although sedan type of cars nowadays are also equipped with spoiler because of the safety and stability it provides. Bernoulli's equation is one of the most important equations in fluid dynamics, and its application can be seen in the study of airflow around the vehicle. Bernoulli's can be stated by this equation: pressure energy plus kinetic energy plus potential energy. In application to our study, Bernoulli's equation principle can help us determine and justify how pressure and velocity varies over the external body of the vehicle. The Bernoulli equation was derived from Newton's momentum equation under these assumptions. In viscid flow, fluid is assumed to be incompressible, density does not change with change in pressure, equation is only applicable along the streamline, steady state is always assumed. Based on the equation, considering that there is no elevation involved, pressure and velocity is inversely proportional to each other. This means when velocity increases at one point along the streamline, the pressure at that point will decrease, and when velocity decreases, the pressure increases. From this, we can also see that conservation of energy can also be a basis for Bernoulli equation. As you can see in the figure, when a body runs at a certain speed, it will break through a barrier of air and it will flow over the body. As the body passes through a region of fluid, velocity and pressure will vary based on the geometry of the body. This means that at some part of the body, we could have a region of high velocity and low pressure, or vice versa. Regardless of the geometry of the body, Bernoulli's principle will still be applicable. Another important principle in aerodynamics is the continuity equation. In application to our study, we will take our fluid to be incompressible. When the fluid is incompressible, there will be no change in the density within the flow. From this, we can infer that at incompressible flow, the mass is not the only thing that is conserved. Even the volume flow rate of the system is conserved. As you can see in the figure, it shows that in a controlled volume, the mass entering and the mass leaving is equal. Generally, continuity equation is mathematically represented by these equations. First is mass of fluid entering is equal to the mass of fluid leaving. Something can also be expressed as density of the fluid entering times the volume flow rate of fluid entering is equal to the density of fluid leaving times the volume flow rate of fluid leaving. If we assume the fluid to be incompressible, the density will be constant and thus the equation will be volume flow rate entering is equal to the volume flow rate of the fluid leaving. This equation can be further expressed as area in the entering side times velocity in the entering side is equals to the area in the leaving side times velocity in the leaving side. Based on this equation, it can be stated that the area of the flow is inversely proportional to the velocity of the fluid. As you can see in the figure, it is a phenomenon called the Venturi effect. We can see that at the top of the surface of the area of the sphere, the area of the flow is lessened, and based on the continuity equation, a decrease in flow area will cause an increase in velocity. Aside from the increase in velocity region at the top of the surface area of the sphere will have experienced a decrease in pressure based on Bernoulli's principle. Taking the continuity equation and Bernoulli's principle into consideration, we can see that a larger surface area is the one that produces the lower pressure region in the system. Along with the Bernoulli's principle and continuity equation, we can explain how and where low pressure and increase in velocity and vice versa will be generated in the system. Moving on, I will now be discussing the aerodynamic forces. First is the lift force and lift force coefficient. In aerodynamics, lift is a force that holds and opposes the weight of a flying object in air. Lift force is a vector quantity. It means that it has a magnitude and direction associated with it. When a lift is generated, it will act upon the center of pressure of the object and it will be induced perpendicular to the direction of the flow. In automobile, the lift is generated when there is a pressure difference in the front end and at the rear end of the car. Lift force equation can be expressed as 1 half times density of the fluid times the velocity of the car squared times the reference area and times the lift coefficient. As you can see in the figure, in a ground vehicle, lift force is generated due to the pressure difference in the front end and the rear end of the ground vehicle. The lift force depends on the density of the fluid, velocity, viscosity, and compressibility, and surface area of the object where the air flows over. The shape of the object and its inclination also influence the amount of lift force to be generated. In aerodynamics, the lift coefficient is a dimensionless number or parameter that takes shape, inclination, and some flow conditions into consideration. Lift coefficient can also be expressed as the ratio of the lift force to the force created with the dynamic pressure times the area. Moving on, I will now be discussing the drag force and drag force coefficient. Drag force is a component of force that acts parallel to the flow as you can see in the figure. Aerodynamic drag force is the one that resists the forwarding motion of the vehicle. Drag force can be expressed as 1 half times the density of the fluid times the velocity of the car squared times the reference area times the drag coefficient. Based on the equation, the drag force is dependent on the square of the velocity. This makes the drag force more predominant when the vehicle is traveling at a very high speed. Another important parameter to consider when it comes to designing the external body of the vehicle is the reference area. When the reference area of the vehicle is large, the drag force that will be induced will also be large, and if the reference area is small, then the drag force will be less. The density of the surrounding fluid also affects the drag force. Then, the denser the fluid is, the higher the drag force that can be induced. In determining the drag force, there are so many factors needed to be considered such as shapes, inclination, and flow conditions. And for simplicity, these complex factors is characterized in one variable called drag coefficient. The drag coefficient can be expressed as the ratio of the drag force to the force produced by multiplying the dynamic pressure and area. In comparison with the lift coefficient, determining the drag coefficient is more complicated because there are more sources of drag such as form-induced wave and ram drag. In our study, we will not include the total drag and will be composed of only form drag. And also in our study, the drag force and the drag coefficient is the most important aerodynamic factor since, since it has an impact on the fuel economy and maximum speed of the vehicle. Moving on, I will now be discussing the source of drag in ground vehicles. The first source is the friction drag. The friction drag force is mainly due to the shear stress on the object. The friction drag produced is also dependent on the orientation of the surface of an object. As you can see in the figure, if the surface of the object is parallel to the flow of the air, the drag force produced comes from the shear stress entirely. If the surface of the object is perpendicular to the flow, the shear force that will be induced will amount to zero. The shear stress induced by the fluid is also related to its viscosity. Viscosity is defined as shear stress required to produce a unit rate of shear strain. Since most of the common fluid has small viscosity, drag is almost negligible since its amount is so small. Another source of drag is a pressure drag. Pressure drag is a component of total drag that is due directly to the pressure induced on an object. The pressure drag is also called the form drag because it is dependent on the form or shape of the object. The pressure drag is mainly generated due to the pressure variation caused by the flow of fluid over the body. Another source of drag is composite drag. The drag coefficient of the car has been reduced significantly over the years, and this is due to the careful design of shape and details of each part of the car. With years of the improving of the aerodynamics design of the car, as you can see in the figure, it is found that there has significant reduction in drag by reducing the frontal projected area of the car. Moving on, I will now be discussing the dimensionless number, which is the Reynolds number. The Reynolds number can be represented by this equation: the density of the fluid times the velocity of the fluid times characteristics of length over dynamic viscosity. The main purpose of the Reynolds number is to become a criterion to distinguish whether the flow is laminar, transient, or turbulent. When the Reynolds number is very small, such as the viscous force is more prevalent, and the effect of inertia can be neglected, this means that the density of the fluid is not that important and can be neglected in the study. When the Reynolds number is too high, the viscous force is so small that we can consider the flow as inviscid. When the Reynolds number is very small, the viscous force is more predominant, and correspondingly shear stress will be large and thus friction drag induced will be high. The opposite happens when the Reynolds number is very large. Beyond Reynolds number of 1000, the friction drag becomes negligible. In application to our study, since the ground vehicle operates at a higher Reynolds number, form drag is more significant than friction drag, and therefore our first priority is to reduce the form drag. Now moving on, I will now be discussing another parameter, which is the Mach number compressibility effect. Mach number is another parameter needed for the drag coefficient of an object. When the velocity of an object is too high, the compressibility effect of the fluid cannot be neglected. The Mach number can be defined as the ratio of the speed of an object to the speed of sound, where u is the flow velocity and c is the speed of sound in the medium, in our case, in air. Mach number has different classification: subsonic, supersonic, hypersonic. Subsonic condition happens when Mach number is less than 1. In the lowest subsonic condition, incompressibility of the fluid can be assumed. When the Mach number is greater than 1 but less than 5, it is called supersonic. At this condition, the compressibility of the fluid is important. For most objects, the drag coefficient will significantly increase at Mach number equals to 1. Now I will now be discussing boundary layer. The difference between the boundary layer and the free stream flow is that in the boundary layer,
The effect of viscosity is more significant because the flow of the fluid near the surface imposes a frictional resistance. As you can see in the figure, as the flow gets near the surface of the object, the velocity of the flow decreases. At the surface, the velocity becomes zero. This condition is called no-slip condition. Another way we can describe the boundary layer is through their thickness. Depending on the condition, the thickness of boundary layer differs. One simple method in determining the thickness is the 99% rule. The boundary layer thickness will be measured from the surface up to the point where the velocity is 99% of the free stream flow's velocity. The 99% boundary layer thickness can be represented by the following function, where u is the velocity of the flow in the boundary layer, where the value is 99% of the free stream velocity, and u sub e is the velocity of the free stream flow. Moving on, I will now be discussing the flow separation. Flow separation or boundary layer separation is a term used when a boundary layer detached from the surface and fluid starts to flow in reverse direction and turns into wake. Flow separation occurs when the area of the flow widens, which will cause decrease in speed and pressure rising. As you can see in the figure, flow separation occurs when there is separation point, and it is also called the inflection point. It exists in the velocity profile of the boundary layer. When the flow separation occurs in a car, a turbulent volume of air is produced at the rear end. This is called afterflow wake or simply wake. Wake is responsible for producing low pressure region at the rear end of the car, and thus it is also responsible for creating a drag or pressure drag. It is also important to note that the size cross-sectional area of the wake can affect the drag. The larger cross-sectional area of the wake is the larger the drag that can be produced. If we want to decrease the pressure drag, we need to delay the separation of the flow. By delaying the separation of flow, we can decrease the drag induced. The reason we want to delay the flow separation is because the earlier the flow separates, the larger the wake will be. By delaying the flow separation, we can decrease the size of the wake, thus decreasing the pressure drag. In a car, we can delay the separation by using a spoiler. As you can see in the two figures, wake region without spoiler has a higher wake area than the wake region with spoiler. Therefore, when spoiler is attached, wake is starting to disperse.
As seen in the figure, the Republic of the Philippines Department of Transportation issued the law RA 4136 to avoid accidents and ensure safety. Violators of the underspeeding or overspeeding will be penalized. Apart from the NAIA Expressway, the minimum speed limit on the country's expressway for generic cars is 60 kph and the maximum speed limit is 100 kph. The list of the minimum and maximum speed for each highway is further identified in the figure. I will now be continuing the report of Chapter 4 Methodology with Rian Garcia. We will now be discussing the methodology of our study and the flowchart. First, we will be configuring the rear spoiler, and after that, we will now validate the AMAD model that is commonly used in CFD simulations to have a better solutions and better results in our studies. Next, we will now be simulating the car model of our study, and then after that, we will document it and then analyze the results of the simulations.
Here we have detailed process for the simulation. It will start with the pre-processing stage. The first step in pre-processing is to define the flow domain, or what we call the enclosure. After that, we need to select what kind of analysis we want to simulate. Next, we will create topological entity sets and define the materials and its properties. The material we are talking about here is the type of fluid we will use for the simulation, and then we will assign boundary conditions. After that, we will specify the number of iterations in numerics in simulation control, and then we will proceed to setting up the results control. In results control, this is where we will specify what data we want to obtain. In our case, it is the drag and lift coefficient. The last step in pre-processing stage is the discretization of domain, or commonly known as mesh generation. This step is important because it has the most impact on the success of simulation. That is why it is important to ensure the quality of mesh generated. If in case the quality of mesh is not good, we need to refine the mesh before we start to simulate. After ensuring the quality of the mesh, we can now simulate and wait for the results. When there is already a result, we can now proceed to the post-processing stage. Then, in this stage, we can validate if the solution of simulation will converge. If it converges, then we will document the results, else we will just increase the number of iterations.
The first step before configuring the rear spoiler, we will be using a sedan car model that's appropriate to our rear spoiler. The sedan car model that will be used in this study is based on Mustafa Kakir.
To design the rear spoiler, first we need to determine the shape of rear spoiler to be used, and then we will solve for the chord width dimension using a given aspect ratio and length of rear spoiler, and then lastly, we will create a rear spoiler support.
The rear spoiler that will be used in this study is flat plate rear spoiler. Aside from the shape of the car, the aspect ratio will be also considered in this study. The aspect ratio that was used in the study is 7.11, which is based from the study of Mustafa Kakir. And the length of the rear spoiler is based on the rear track width of the car, which is 500 millimeters. We will now be getting the chord width of the rear spoiler by dividing the aspect ratio of 7.11 to the length of the rear spoiler of the 500 millimeters, and we will be getting 70.32 millimeters, which is the chord width of the rear spoiler. To meet the objectives of the study, we will be simulating different setups of angle and height of the rear spoiler at this sedan car. The maximum height of the rear spoiler that we'll be using is 89.85 millimeters, which is perpendicular from the stand of the rear spoiler to the roof of the vehicle. And for the angle, we will be using -4 degree, -2 degree, 0 degree, 2 degree, and 4 degree angle. After successfully configuring the rear spoiler, we will now be validating our simulation by using the AMED model and simulating it in SimScale Safety simulations. The AMED model is seen in the slide, and the simulation settings for the validation is also seen in this slide, and the computational domain that will be used in this study is the upstream, which is 2 times the length of the car, and the downstream, which is 6 times the length of the car, and lateral directions, which is 2 times and the length of the car.
So, for us to perform CFD analysis, we need first to set up our boundary value problem and perform discretization of domain. So, those things can be done in pre-processing stage. So, the first thing that we need to do is to set up our domain, and that can be done by defining the enclosure. The box that we are seeing in this slide is our enclosure or our domain. So inside this enclosure, the fluid will flow. These are the coordinates of our enclosure. After we set up our domain, we will now select what kind of analysis we want. In SimScale Workbench, we can either choose flow or structural. In our case, we will select the incompressible fluid flow. If we're going to look at the description under incompressible fluid flow, we can see here that this is for a fluid with a speed less than 100 meters per second at standard pressure. And this is also for an assumption of constant density. Since that's the thing we stated on our chapter 1, I can say that incompressible fluid flow is the most suitable analysis type for us. To make our simulation more realistic, We will also account for the turbulence of the flow, and we can do that by selecting a turbulence model. For us, we will select the K omega SST model. There are two reasons why we select or choose the K omega SST as our turbulence model. One reason is that this is for low velocity and low Reynolds number application. Another thing is that usually the K omega SST model is recommended for most external aerodynamic study. We also need to select the time dependency of our analysis. So for our simulation study, the time dependency would be steady state. The reason for this is because in steady state condition, the data wouldn't change with respect to time, and this will make our data gathering more convenient. Next, we have creating topological entity sets. So usually, after being done with the defining of enclosure and selection of analysis type, we proceed to defining the materials and assigning of boundary conditions. But we would still create topological entity sets even though it is not necessary because it is a good practice. So when we say topological entity sets, these are group of entities. So these entities can be either volume, faces, or edges, and it can also be nodes.
In our study, we will only be using one topological entity set, and it is the car body.
We have the body of a car as one of our topological entity set. We can also select what kind of fluid we want for our simulation. So for our study, we will use air as our fluid, and for its properties, we will set it to default setting. We will now assign boundary conditions. Boundary conditions are initial conditions we use to solve for the dependent variable along the domain. In our case, that dependent variable would be the velocity and pressure. In our flow domain, we will have a total of 6 boundary conditions. On the enclosure surface in front of the car, we will assign the velocity inlet boundary condition. Velocity inlet is where the fluid will start to flow, and it will have a velocity of 120 kilometers per hour or 33.33 meters per second as we stated in our chapter 1. The reason for this is because at this speed, it will be easier for us to assess the aerodynamic performance of different cars configuration because at a speed lower than this, at a speed lower than 120 kilometers per hour, the aerodynamic performance of different cars configuration will not differ that much. So that's the reason why we set it to 120 kilometers per hour. At the opposite of velocity inlet, we have the pressure outlet. So the value of our pressure in the pressure outlet would be the atmospheric pressure. So it will have a value of 101.325 kilopascal or zero gauge pressure. The purpose of pressure outlet is to serve as a basis for the pressure variation along the domain. For the top wall and the wall adjacent to it, We will assign a sleep wall boundary condition. By assigning a sleep wall boundary condition to these two walls, they will become frictionless, and thus the velocity of the flow on the surface of these two walls will be the same as the velocity of our inlet, which is 33.33 meters per second. In CFD simulation, the larger the object we want to simulate, the longer it takes for the simulation tool to solve for the parameters we want. That's why if we have a symmetrical object, we will only simulate half of the object and apply symmetry boundary condition to it so that the result that we can obtain in simulation will be as if we simulate the whole object.
To simulate a moving car, we will now be assigning a no-slip condition of the wall which is tangent to the wheels of the car. This will be act as the road where the car would be moving at a high speed scenario.
For the body of the car, we will assign a no-slip wall boundary condition to it because it is not frictionless. And by doing so, the concept of boundary layer will be applicable to it, and that means the velocity of the flow on the surface of the car will be zero. After assigning all necessary boundary conditions, we will now set up our simulation control parameters. So here, we will specify how many iterations we want, and we can control the number of iterations with n time and delta t. For a more simple approach, we will let our delta t to be equal to 1. And in n time, this is where we will set the number of iteration we want. Since a 1000 iteration is enough for most CFD simulation to get a decent result, we will set our end time to 1000. The drag and lift coefficient is commonly used to assess the aerodynamic performance of the car. And for us to obtain those data, we just need to set it up in our results control. For our simulation tool to solve for drag and lift coefficient, we just need to define their parameters in results control. So we have the free stream velocity, reference length, and reference area value. The drag and lift coefficient will have a same free stream velocity and reference length, but they will have a different reference area value. For the drag coefficient, we will use the frontal area as our reference area, while to solve for lift coefficient, we will use the wing area as our reference area. We will now discretize our domain. When we perform discretization of domain, what we are actually doing is we are dividing the whole domain, flow domain, and geometrical domain into section of elements. And just like I said earlier, discretization of domain is important because this method is the one that made the CFD analysis possible. Another term for discretization of domain is generation of the mesh. The reason why we refer a discretized domain as a mesh is because of its network-like structure. When it comes to generation of the mesh, we are concerned with two things. One is its fineness, and the other one is the number of processors. The fineness of the mesh is dependent on the number of elements and its size. Usually, the more number of elements we have, the smaller its size could be. And now, for the number of processors, it indicates how fast the simulation process will be. So if we have a high number of processors, that means that our simulation process will be faster. The most important thing here is to get the balance between the fineness of the mesh and number of processors. while ensuring the quality of the mesh. To obtain a reliable CFD results, it is important that the mesh quality is good. And for us to determine the quality of the mesh, we need to rely on mesh quality metrics. For mesh quality metrics, we have the aspect ratio, non-orthogonality, edge ratio, and volume ratio. For the aspect ratio, edge ratio, and volume ratio, the recommended range is less than 100, while for non-orthogonality, it should be less than 75. We can refine the mesh of a certain volume we want. In our case, we want to refine the mesh around the car, and that can be done by setting up the maximum edge length of each element of the mesh. By setting up the maximum edge length, we can control the size of elements inside our chosen volume. After defining the domain, selecting a type of analysis we want, assign boundary conditions, and generating the mesh, we can now start the simulation process. After the simulation process, we can now proceed to post-processing stage. In post-processing, we can visualize and get the results of simulation. We can visualize how pressure and velocity varies over the domain. And for the results of simulation, since we specify in the results control that we want the drag and lift coefficient, we can obtain those data in post-processing. Aside from visualizing and getting the results of simulation, we can also verify our results in post-processing. We can verify if the solution of our simulation will converge. Having a converged solution means that the results of successive iterations will have a relatively small discrepancy from preceding iteration. One way to check for the convergence is to look at the graph of the results. So here we have the plot of drag coefficient for 1000 iterations. We can notice here that at around 900 iteration, our solution starts to converge. Another way we can check the convergence is to check the residuals graph. Residuals are solution imbalances. They are used as a measure for discrepancy between each iteration. Now, if we want to reach convergence, we want our residual level to decrease as we go further with our iteration. Usually, at below 1 times 10 raised to negative 3 level, we can already have a converged solution. Aside from checking the convergence, we can also check the consistency of the result in residuals graph. Now, if we can see a lot of fluctuations in the graph, we can say that the result is not consistent and we cannot get a reliable results from it. If we are still not convinced with the results of our simulation, we can do two things. We can either increase the number of iteration or refine the mesh again. Usually for incompressible fluid flow simulation, these two is enough for us to reach a convergence. Now, if we are already satisfied with our results, we will document those results for further analysis. I am Rian Garcia, and I'll discuss the results in discussion. In the methodology of this study, it is stated that we need to validate the computational domain and the turbulence model we will use with our simulation setup. The validation will be done with a model that has an experimental result. In our case, we will use the Ahmed body geometry. Based on what we see from different study, this model is usually used for validation purposes. The experimental drag coefficient of the Ahmed body is 0.298, and our simulated drag coefficient in sim scale is 0.31, which results to 4.03% error. Here we have the drag coefficient plot of the Ahmed's body in sim scale workbench. So we can see in this plot that at around 1500 iteration, it already converged. In order to assess the effect of rear spoiler to aerodynamic performance of the car, the researcher will perform the simulation first to a car without rear spoiler. The resulting drag and lift coefficient of the car without rear spoiler will serve as the benchmark for comparison of performance of all car model with rear spoiler setup. So here, at 80 kilometers per hour, our drag coefficient for the car without rear spoiler is 0.34, and its corresponding lift coefficient is 0.14. And if we proceed to 100 kilometers per hour, the drag coefficient will remain the same, while the lift coefficient will increase from 0.14 to 0.16. And after that, when we go to 120 kilometers per hour, we will see that there's an increase in drag coefficient. It become 0.37, and its corresponding lift coefficient is 0.19. Velocity distribution can help us visualize the flow around our car model. It can give us important information such as the size of low pressure zone. Low pressure zone is located at the rear of the car. A larger low pressure zone means that the drag induced in the car is high. Here we can see that the low pressure zone for a car without rear spoiler doesn't change as we transition from 80 kilometers per hour to 100 kilometers per hour. This makes sense because from the results, the drag coefficient at 80 kph and 100 kph are the same. When the speed goes to 120 kph, we started to see a little bit increase in the low pressure zone of our car. This is why the drag coefficient got increased from 0.34 to 0.37. Next, we have the drag and lift coefficient of a car with rear spoiler. In total, we have 20 rear spoiler setups. So we have 4 different heights and 5 different angles. Since our benchmark is simulated in 80 kph, 100 kph, and 120 kph speed, we will also do the same for the car with rear spoiler. The graph we are seeing now is the drag coefficient summary of all rear spoiler setup at 80 kph speed. In the graph, we can see that most of the setup has a higher drag coefficient compared to our benchmark, except when the height is either 22.46 mm or 44.925 mm, both at -4 degree angle. So the drag coefficient of that setup is 0.33, which is lower by 2.94% compared to the benchmark. So this is the velocity distribution of a car with a rear spoiler whose height is 44.925 mm at an angle of -4 degrees. If we compare this from the velocity distribution of the benchmark, we can actually see a decrease in low pressure zone. making the drag coefficient of making the drag coefficient of this rear spoiler setup lower. For the lift coefficient of all rear spoiler setup at 80 kph, we can see that regardless of height or angle, the result will be lower compared to our benchmark. The highest lift reduction occurs when the height of rear spoiler is 22.46 mm and the angle is 4 degrees. In 100 kph, improvement in drag coefficient only happens when the rear spoiler's height is either 22.46 mm or 44.925 mm, both at an angle of -4 degree, just like the result we got from 80 kph. Aside from that setup, all setup results to higher drag coefficient compared to its benchmark. Earlier, we discussed the velocity distribution of a car with a rear spoiler whose height is 44.925 mm at -4 degree angle running at 80 kph. Now, when the speed becomes 100 kph, we can see the velocity distribution doesn't change that much. That is why the resulting drag coefficient at 80 kph and 100 kph didn't differ that much. When the speed is 100 kph, um, all the lift coefficient of all rear spoiler setup is still better or lower compared to its benchmark. And just like in 80 kph, the highest reduction in lift can still be found when the rear spoiler's height is 22.46 mm at 4 degree angle. For 120 kph, the setup that results the lowest drag coefficient is still the same, just like in 80 kph and 100 kph. The rear spoiler's height is either 22.46 mm or 44.925 mm, both at an angle of -4 degree. Earlier, we observed the velocity distribution of a car whose spoiler's height is 44.925 mm at -4 degree angle when the speed is 80 and 100 kph. Now, what we have in this slide is the velocity distribution of that setup, but at 120 kph. We can notice here that there's almost no change in velocity distribution from the velocity distribution of 80 kph and 100 kph. Now, for the lift coefficients of all rear spoiler setups at 120 kph, just like the results we have in 80 and 100 kph, everything improves, and the setup that has the lowest lift coefficient remains the same. In 80 and 100 kph, the lowest lift occurs at 22.46 at 4 degree angle. You can also say the same for 120 kph. Next, let's analyze how drag and lift coefficient varies as the speed increases. What we have here is the speed versus percent change of lift coefficient. Let's use the setup whose rear spoiler's height is 22.46 at 4 degree angle. Looking at the chart, we can see that the percent change is increasing in negative direction as we go from 80 kph to 120 kph. This means that the effect of rear spoiler in decreasing the lift coefficient of the car gets more significant as the speed increases. It is also important to take note that This chart represents the result of all other setup. Even though numerically it is not the same, we can still expect to see a same pattern just like what we have here. The two charts we have here summarizes how drag coefficient varies for all simulated rear spoiler setups as we transition from 80 kph to 120 kph speed. So when the speed goes from 80 kph to 100 kph, the drag coefficient either remains the same or got increased. And then, regardless whether the rear spoiler is effective in decreasing the drag from benchmark, it will still experience a decrease in drag once we go from 100 kph to 120 kph. Next, we have conclusion. The researchers were able to configure a flat plate rear spoiler based on the study of Mustafa Kakir. Using the same scale CFD simulation tool, the researchers were able to show the effect of rear spoilers' different height at varying angle to the drag and lift coefficient of the car. In all speed, 80 kph, 100 kph, and 120 kph, the lowest drag coefficient occurs when the rear spoiler's height is either 22.46 mm or 44.925 mm, both at -4 degree angle. In all speed, from 80 kph to 120 kph, the lowest lift coefficient occurs when the rear spoiler's height is 22.46 mm at +4 degree angle. Based on the results, we can also conclude that the drag coefficient will either increase or remain the same when the speed goes from 80 kph to 100 kph. Once the speed reaches 120 kph, the resulting drag coefficient will be lower compared to the result in 100 kph. Even though the drag coefficient got decreased as we go to 120 kph, it doesn't mean that the result is lower compared to the benchmark. Regardless of the drag coefficient results, all cars with rear spoiler setups have improved in terms of lift coefficient. For any rear spoiler setup, the percent reduction of lift rises as the speed increases.